The aims of these set of videos are fourfold. 1. Explain how Bootstrap samples are generated. 2. Explain the MAC method. 3. Show how Bootstrap samples can be used to test the MAC method. And 4. Compare MAC Bootstrap samples with optimal PTF Bootstrap samples. The MAC method is a regression formulation of volume-weighted average link ratios. Volume-weighted average link ratios in Europe are termed the chain letter method. A link ratio is one number divided by another number. And as a result of that, a link ratio is the same as the slope of a line, or it's a trend line. Therefore, average link ratios, weighted average link ratios, arithmetic averages, any type of average link ratio is an average trend line. It's equivalent to an average trend line. So MAC in 1993 formulated volume-weighted average link ratios as a regression estimator, or as a regression line. What's the advantages of formulating volume-weighted averages as regression estimators? When you formulate them as regression estimators, the assumptions you make in the model are transparent, they are clear, and that allows you to test the assumptions whether they're supported by the data. Another thing is that if you look at the assumptions which are stochastic, if the model does work for the data, the method does work for the data, you can calculate other statistics like standard deviations of reserve distributions. Now, the idea behind the Bootstrap is an old one. It is a resampling technique that was popularized by Brett Ephron in 1979. It is now a celebrated paper in the Annals of Statistics. Ephron drew our attention to the Bootstrap's considerable promise and actually gave it its name. The Bootstrap, actually, the whole idea is actually older than 1979. It goes back to the 50s, but because it's computer intensive in terms of recalculating, resampling from your sample. It involves a lot of computing power, and at that time the approach was regarded kind of as unthinkable. It only became thinkable when we started having a lot of computer power. The Bootstrap technique is used to calculate standard errors of parameters, confidence intervals, distributions of forecast, and so on. Typically it is used when the sample size is small so that distributional assumptions cannot be tested and asymptotic results are not applicable. It also has applications to large sample sizes where distributional and model assumptions can be tested, but the mathematics for computing forecast distributions becomes untenable. Bootstrap samples of the MAC method provide another compelling reason amongst the numerous others why it does not work. That is, it gives grossly inaccurate assessment of the risks. Incidentally, this particular PowerPoint display is also available on our website where you've located this particular video. So what's the underlying idea of the Bootstrap? Suppose you have a set of observations, but you don't know the distribution of the observations, and parametric distributional assumptions cannot be tested. And that's usually the case if the sample is small. So in these simple cases, where all observations come from the same distribution, the best estimate of that distribution is just a sample distribution function. So you calculate the sample distribution function. It's a bit like a frequency graph or a histogram. And what you might want to do now is, using your sample distribution function, you want to calculate a particular percentile. So you might calculate the 90th percentile. But you don't know the uncertainty or the standard error or the standard deviation of that percentile. So what you can actually do is draw other samples from your original sample. So you have a sample of n observations, and now you're going to draw other samples or create other samples that we call bootstrap samples or pseudo data, where you're actually going to draw it with replacement. So you select one observation at random amongst the n observations, and that's the first value in your bootstrap sample. You put that back into your flask, and then you draw another one at random. So now your first bootstrap sample will not be identical to the original sample because you're withdrawing with replacement. And you keep on repeating that operation of creating bootstrap samples many times, 1,000 times. And then you can calculate your 90th percentile for each one of the bootstrap samples. And the volatility in that 90th percentile estimate will give you an idea of the standard error of the percentile. It's quite an interesting idea, and it seems like you're sort of getting a lot from nothing. And in fact, the term bootstrap conveys the impression of something for nothing, as you are resampling from the sample. But you've already got the sample, so how are you actually extracting more information? You might have as much success as pulling yourself up by your bootstraps, and that's the reason for the origin of the term bootstrapping. But that is actually not the case. You can in fact extract more information from your sample by resampling from your sample. And the whole idea is pretty simple. I mean, the resampling operation that's with replacement, it's a pretty simple idea. But what if instead, the first case we actually looked at is if you had independent observations that came from the same distribution. But what if your data, your observations, don't come from the same distribution? So that you could actually write an observation as equal to, let me just say here, is equal to a mean. So each observation does not have the same distribution because each observation has a different mean, plus what's called an error term. And that error term has a distribution with mean 0 and some variance. Let's suppose that. And you're not going to make any distributional assumption about this error term, perhaps because you can't test it. So what you're going to do now is, instead of creating bootstrap samples from the original data, you actually create bootstrap samples from what I call the residuals, the estimates of these terms. So the residuals are sampled with replacement and reallocated to the fitted values to form pseudo-observations. More of this in detail in subsequent transparencies. Okay, you might have to rescale the residuals based on their variances. So typically, in a lot of actual applications, it's the residuals which are actually resampled, or we create bootstrap samples or pseudo samples of the residuals. Now, what is the comparison between bootstrap samples and the real data? If the model is correct, a pseudo sample should have the same characteristics as the real sample. That means that the real data should be indistinguishable from the bootstrap sample in respect of trend structure and volatility about the trend structure. If there is a difference between the bootstrap sample in terms of volatility with the real data, then the bootstrap sample is no longer useful because it was generated by a model that didn't represent the features in the data. And this is a very important idea. I mean, most actuaries use the bootstrap technique to calculate various statistics, like applying the MAC method, the bootstrap to the MAC method. They calculate standard deviations, distributions of reserves. We're using the bootstrap in a very different sort of way. We're actually using the bootstrap by looking at the bootstrap samples and saying, do they actually match the data in respect of the features of the data? And if there's a mismatch, there's something wrong with the model. Remember that the bootstrap technique is not a model, and it doesn't make a bad model good. It should only be used once you've tested all the assumptions of the model are supported by the data. Okay, so we're going to compare Bootstrap samples from the MAC method and related methods versus Bootstrap samples based on the optimal PTF model. And what we're going to find in many cases that the Bootstrap samples based on the MAC method do not reflect the features in the real data. In other words, you can easily distinguish between the real data and the Bootstrap samples. It tells you there's something wrong with the method. There's something in the data, some features in the data that the method doesn't capture, or there's some features in the method, but they're not in the data. However, you cannot distinguish between Bootstrap samples based on the optimal PTF model and the real data. In subsequent videos, we are going to give an overview of the MAC method. We're going to give an overview of the probabilistic trend family modeling framework, and there are more details and more detailed videos that we'll explain in the next video on our website. Okay, so which examples, real-life examples we're going to look at? We're going to look at 3 real-life examples. We're going to look at the triangle group, a TG, which is called ABC, Bootstrap, BS for Bootstrap. And ABC really is workers' comp, large US carrier, and it's got a major calendar year trend shift. Okay, and you'll even see that when you apply the MAC method to it, because you'll be looking at residuals versus calendar year, and you'll see a very strong trend change that even the MAC method indicates if it is applied in a regression context. Another triangle group, L link ratio LR high, the MAC method gives a mean reserve which is perhaps too high by a factor of 2, so that you'll see that the MAC method measures a trend in the data which is much larger than the actual trend in the data. So it forecasts reserves using a trend which is much higher than the trend in the data. Whereas for triangle group TG, adverse tree, homeowners, farm owners, it's the other way around. This is LR high, the trend in the MAC method versus calendar years. For this one, the MAC method measures a trend which is much less than the trend in the data. So this is what the trend in the residuals looks like. We'll explain all that in detail later. And as a result of that, the MAC method gives an answer which is wide off the mark, and it's perhaps a third or quarter of what should be the true mean of the reserves. All data sets are real with changing calendar year trends. In each case, it is shown that the MAC method doesn't capture calendar year trends, and the corresponding Bootstrap samples bear no resemblance to the real data. So notwithstanding the fact that for each one of these real data sets, the MAC method gives false indications, false indicative reserves, false indications, and so on of what's going on in the business. But apart from that, we've got further evidence that doesn't work by looking at the Bootstrap samples. Of course, this is not the case with the optimal PTF model. So let's go back and try and describe the Bootstrap, how you create Bootstrap samples in a bit more detail. Suppose you've got some data, y sub I equals 1 to n. The model can be expressed as, it's a linear model. Suppose y sub I equals mu sub I plus an error term. Mu sub I, that's the mean for observation I, could be a function of a number of predictor variables. So for instance, in a linear regression, mu sub I might be, say, alpha plus beta. In a straight line regression, x sub I. That's one possibility for the specification of mu sub I for linear regression model. Okay, I mean, mu sub I could be a function of a number of predictor variables. X sub I is called a predictor variable or an independent variable. So we're kind of generalizing. Mu sub I could be a function of a number of predictor variables. The error term, incidentally, is a integral part of the model. Okay, so then you're using some optimization criterion. It could be maximum likelihood, weighted least squares, or whatever. You fit the mean values y sub I, and the fitted value is y sub I with a hat, and the corresponding fitted value to the data is y hat sub I. Okay, so you've got fitted values now for your data. The residuals are the differences between the observed and the fitted values. So EI is the observation minus its corresponding fitted value. So if you've got a straight line, if mu sub I is alpha plus xi, you've got some observations. You've fitted this line using least squares, and these are the fitted values. These are then the residuals. Some are positive, some are negative. So let's just continue with the model again. Just a specification of the model. Mu sub I might depend on it's a function of a number of parameters and predictor variables. It might specify some kind of trends in the observational data. Epsilon I are termed the error terms and represent the volatility in the data about the trend. In the parametric model, you actually make an assumption about the distribution of the error term. It might be normal, it might be Pareto, or whatever, okay? But in the context of the Bootstrap, you're kind of arguing, well, I can't make test any distributional assumptions, or if I want to make the model non-parametric, let's not assume any distribution for the error term, and this is in the context we use the Bootstrap. If you make a parametric assumption, distributional assumption about the error term, suppose you assume it's normal, and you test it using the data, and the test passes. There's no indication that it isn't normal. You don't reject that hypothesis. Then the answers you get based on Bootstrap sampling, say for the distributional forecast, will be the same as the parametric model. So there's no need then to do the Bootstrap. Okay? But let's suppose you want to keep it non-parametric, and you don't have enough data to test these assumptions. So now the variance of the error term is an integral part of the model, and it sort of represents the process variability. Most importantly, the model assumes that the standardized errors are random from a single distribution with mean 0. Okay, that's an assumption of the model, but it's got to be true also for the data once you fit the model. This also applies to the standardized residuals. The residuals, let's look at those again, and this is a very important interpretation of the residuals. The residuals should be interpreted in the following way. The residuals represent the trends in the data minus the trends estimated by the model. Very important. The residuals can be thought of as the trends in the data, or the data adjusted for what we fitted to the data. If you understand the model, you know what you've fitted to the data, and you're looking at the data adjusted for what you fitted. That's what the residuals represent. If you find that too difficult, just think of it trends in data minus trends estimated by the method. That's all. It's the difference of two trends. Okay. You normally would calculate the standardized residuals, so you put them on make them comparable by dividing by the standard deviation of the residual. And you're assuming that the standardized residuals are independent and drawn from a single distribution. So now you have a random sample from some distribution with mean 0. So let's see now. How do you create your Bootstrap sample? You've got an observation data equals the fitted value plus the residual. Okay, or if you like, you might remember that the residual equals yi, the data, minus the fit. So the data equals the fit plus the residual. You put all your residuals in a flask, and now you draw them randomly with replacement. So you draw the first one. Let's call it E1 star. Now, this E1 star might correspond to the, say, data number 7, observation number 7, E7. But now you're going to assign E7, so if this is 1 here, if you put that 1, the first bootstrap observation corresponding to the fit for observation 1 and E1 star, but E1 star is going to equal E7. So you're kind of reshuffling your residuals and reallocate them to the fitted values. Let's go to the second one. Pretty simple procedure. Okay, then you draw your second one. You put this one back in, you draw a second one with replacement, and this is this one. And this could be, say, the residual that corresponds to the 9th observation, E9. So now you've got a 2 here. The second observation in your bootstrap sample is the second fitted value, but it's the 9th residual, okay? E9, and so on. So you have a bootstrap sample now equals the fit plus the resample residuals, and usually scaled based on standard deviation. So it's pretty easy to then create the bootstrap data from the bootstrap residuals. What about for a triangle? Well, it's the same idea. You have a triangle of data, which we call Y values. You have an observation in every cell. Each observation is called a Y value. You have corresponding fitted values based on the model that you fitted using either weighted least squares, maximum likelihood, or whatever. And as a result, you've got a residual in every cell. Now you've got to recreate a resampled triangle of bootstrap residuals. What you do is you take a residual at random from the flask and put it into the first cell. Then you take another residual at random from the flask after you replace that one and put it in the second cell. And keep on doing that, always with replacement, until you have what's called a bootstrap triangle of residuals. You grab it, put it there, add it to the fitted values to create a new sample data called bootstrap data or pseudo data. If you want to create another bootstrap triangle of data, well, you repeat the operation. You start creating this bootstrap sample of residuals by selecting with replacement from the flask. Create a second one, put it there, plus add it to the fitted values which are there to create a new set, and so on. So the procedure is pretty easy, but you can see at the time when you didn't have computers, it was kind of unthinkable to do something like that, especially if you want to repeat it 10,000 times. Now the bootstrap technique actually goes further. We're not looking at the whole bootstrap technique. The bootstrap technique, if you're applying this to Mac, would re-estimate Mac to each one of the bootstrap triangles, and then by looking at the volatility or how the answers change, you get an idea of the distribution of the reserves. Okay, but we're not really needing to look at that step, and the reason for that is because we're just going to look at the bootstrap samples, these bootstrap samples, and compare them to the original data. Do they have similar characteristics? So the bootstrap technique only works if the model works. If the model doesn't work, then it's like putting more cards on a house of cards. Okay, so let's look at an example here, which you can also run using your PowerPoint display, again available from our website. Let's suppose that our model is fitting two trend lines with random volatility about the trends. In fact, that's the way the data was originally simulated, using two trend lines, two distinct trend lines. So this data is random around two trend lines. Okay, so we've got some data. The data is listed as y sub I. Got n observations, say, and I guess the horizontal axis, the x-axis, is just time. So you can think of the linear part of the model, mu sub I, as being two straight lines. It's one line here. Okay, so that would be, say, alpha 1 plus beta 1 xi, where x is on, so it could be, say, alpha 1 plus beta 1 x1 xi, say. Okay, beta 1. But then it's a different line. That's for values of x's in this interval. But for values of x's in that interval, it's a different line. But the two lines don't have 4 parameters because they intersect, say, at period 6, so they really only have 3 parameters. Okay, you've got random errors. That's an assumption. In fact, that was the way the data was generated. Now you fit 2 lines, intersecting, I guess, there. And once you've done that, you've got 2 fitted lines, and these are the fitted values here. These are just bands. What we've calculated here is the standard deviation of the residuals, and then we took, say, 1 standard deviation, 2 standard deviations, 3 standard deviations. So these contours just represent sort of the spread of the residuals. Okay. We now have residuals, which are the observed. For instance, that's a positive residual, that's a negative residual. That's a positive, that's a large negative in absolute terms. That's a positive residual, negative residuals. So we have all these residuals. We then stick them on the x-axis, and for instance, you could see that the residual for this observation here is large and positive, right? The residual at 4 is small, okay? All right, so at 4, the residuals is here, okay? Now, I guess we're going to reshuffle the residuals. Can you see? All of a sudden, the residual of 4 is this negative one. Let's reshuffle again. Just doing it a few times, okay? Well, the residual of 4 now, I guess, is positive. But that wasn't, I mean, that's the one we've now reallocated to period 4. But the actual residual from memory, I think, was negative, wasn't it? Let's just see. No. Yeah, the actual residual of 4 was negative, okay? It was negative. But now we're going to assign it, one of the other residuals here will drop into this particular period. That'll be the bootstrap residual. Okay, so it's going to be positive there, and it's come from one of the other ones. So now we add all those bootstrap residuals to the fitted values. Okay, so we've moved them up. You can do this yourself in the PowerPoint display. And then we get a new set of fitted values, observed values, which is the pseudo data or the bootstrap data. So now that's a new value there. Was originally the actual data is down below there. So the new datum is there now, and so on. Okay, so the blues are I think the light blues are the original data, and the new blues are the darker blue is the bootstrap sample, and you can repeat this many times to get many bootstrap samples. And then you can fit the 2 straight lines to the bootstrap samples. Don't worry about this kink here. I don't know. It's an artifact of what Excel did, which there should be only 2 lines rather than this third one sort of bottoming out here. Bottoming out here. So you can see that the bootstrap samples look almost the same as the real data. Suppose instead you decided to fit just 1 line, 1 single line regression model. We know that the data actually behaves this way, the real data. Now let's calculate the residual based on the straight line. If you calculate those are the residuals, and you'll notice that a lot of these are mostly positive, these are mostly negative, and these become mostly more positive, right? So if you look at the residuals scale slightly, that's what they look like. I'm going to scale them that way. So these residuals have a negative trend, and these residuals have a positive trend. Well, that kind of makes sense. Let's see what's happening. If you interpret residuals now, residuals represent the trend in the data minus the trend in the method. For these periods, the trend in the data is less than the average trend. The average trend is a single line. In these periods, the trend in the data is higher than the average trend. So for the early periods, residuals, trend in data minus trend estimated by the method is negative. Trend in data minus trend by method, which is larger, is negative. For these periods, trend by method, estimated by the method, trend in data minus trend estimated by the method is positive. Okay, residuals is trend in data minus trend estimated, and this is why you get V-shaped. Trend in data minus trend, average trend is negative. Trend in data minus average trend is positive. If you now resample from those many times and you estimate two straight lines, you just get two straight lines. One straight line, you get one straight line. But if you estimate two straight lines to the Bootstrap samples, there's no change in trend. But there is a change in trend in the real data. So here you can start distinguishing immediately between the real data and the Bootstrap samples based on one straight line rather than two straight lines. And then it indicates to you that the model one straight line is not appropriate for this data set because it actually has two distinct trends. Thank you.